Assalamu alaikum, my grade 8 boys and possibly girls who are watching. I would love to say hello and welcome to the new unit, which is physics. Alhamdulillah, as you know, this is my favorite unit. And we're going to be starting this unit by talking about motion, which is simply movement, or a bit more than that. So, what does the word motion mean? Motion, what does it mean? Now, you might be tempted to say, well, motion, an object is in motion if it's just sort of moving. So let's say, for example, if I'm sitting in my place and I'm wiggling about, am I moving? Some of you might be saying, yeah, you're moving, you're in motion. But strictly speaking, from a physics standpoint, when we talk about motion, we mean change in position. Change in position. So if an object changes position from over here to over here, then it's in motion. If it doesn't change position, then we don't really say that it's in motion. Okay? So when we talking about motion, we mean change in position. Okay? So start with that. Moving on. So here we have Nicholas Copernicus, who is Polish, I believe. So why would anyone think that Earth moves around the sun? After all, on a clear day, you can see the sun move across the sky. The sun move across the sky. But Polish astronomer, he is Polish, Nicholas Copernicus realized that an object revolving around you from left to right looks the same as an object standing still while you rotate from right to left. In On Revelation of Heaven Spheres, he wrote, every apparent change in respect of position is due to the motion of the object observed, or of the observer, or indeed to an unequal change of both. Okay, so what that means is just sort of a fancy way of saying. So even though it might seem like things are moving around you, realistically speaking, it is possible that you are moving around yourself, which is true, of course. Now, if I'm rotating around this chair, it looks like the room is rotating around me. But we both know that it's not the room that's moving, it is I. I am moving. So over here we've got a question that says, write your answer to the question below. For thousands of years, many people thought Earth was the center of the universe. Name one possible reason why they thought this. Well, it's quite simple, really. They saw everything was, or seemed like it was rotating around the Earth. Because it looked like everything in the sky, in the sky, and that includes everything in the sky, which includes the sun, the moon, the stars, revolved around the Earth. Revolved around the Earth. Okay, that's what it looked like. Let's move on. So what does motion mean? An object is moving or in motion when its position changes relative to a reference point. Now this here is a new word or new vocabulary terminology that we need to know about. What is reference point? A reference point or a point of reference is something we measure our movement against. Okay, so let's say for example I'm sitting on a train. If I'm sitting on a train and I'm sitting next to my friend, and we're both just sitting down chilling as the train is moving. Now I look around and I look at him. I look at him, and he's not really changing position. We're both moving because the train is moving, but at the same time we're both not moving because we're next to each other. What's going on here? Well, it depends on the reference point. If we measure our movement against somebody standing outside the train, then we're definitely moving. Someone outside the train might look at us and say, yeah, the train is moving, and you are moving because you're in the train. However, somebody inside the train would look at us and say, no, you're not moving. Okay, so if I look at my friend, I can see that they're not moving. And so that's what we mean by reference point. What we're measuring against. What is the marker? Okay? So if you look at this example here, we've got what looks like a Land Cruiser. No, sorry, it's probably a Range Rover actually. But it's not moving relative to anything. But then as soon as I click on it, is it going to move? Is it going to do it? Nope, it's not going to do it. Um, that's the reference point. If we take the tree as a reference point, the car's in motion when its position changes relative to the reference point. So is it going to change? Now it's changing, therefore now it's moving. Okay? It's changing relative to the tree. And if the tree wasn't there, then we'd have to find another reference point. Another example I want to tell you about is, say for example you're on the plane. The plane is moving at a speed of about 1,000 kilometers per hour, which is very fast. 1,000 kilometers every hour. However, if you're looking at the plane from sort of somewhere on the ground, you could see that the plane is moving very, very fast. Yeah? However, you could be sitting on the plane and sleeping, which a lot of people do. So you could actually, in fact, be sleeping and still be moving. How? Well, relative to the plane, you're not moving. Relative to every other passenger on the plane, you're not moving. So as you are sitting down enjoying your meal, or as you're sitting down watching a movie, or if you're sitting down sleeping on the plane, you're not really moving relative to that reference point, i.e. the passenger on the plane or the plane itself. You're not moving relative to that, but you are moving relative to everything else outside the plane. So that's what we mean by a reference point. A reference point is a marker, a reference point is the observer, a reference point is something we measure our movement against. Okay, let's move on, and I'm sure as we do more examples, hopefully it'll become a bit more clear. When is an object in motion? So we've already talked about this, but I'm just going to reinforce this idea. Deciding if an object is in motion isn't, excuse me, just a second. Deciding if an object is in motion isn't as easy as you might think. For example, you're probably sitting in a chair as you read this book. Are you moving? Well, you might think that you're not moving. However, parts of you are moving. Your eyes blink and your chest moves up and down. But you would probably say that you're not moving. Because remember, we talked about that example about wiggling. So movement, in terms of physics, motion is if the position changes relative to another object. Okay? Because your position relative to your chair does not change, you could say that you're not really in motion. Okay? Let's move on here. So here's what I want you to do. I want you to write down at least 2 examples of objects in motion and identify their reference point. Okay, so I want you to take a minute to think about this. Pause the video if you have to. Think of 2 objects that are in motion and identify their reference points. Okay, so I'll give you an example. The Earth is in motion, and the reference point we could use is the sun. Or we could say, for example, a rocket is moving across the sky, and the reference point is Earth, right? It's moving relative to Earth. Or the clouds moving across the sky relative to the ground. Or we could say the cat's moving relative to the tree. Or we could say the car's moving relative to the traffic light because it's moved and the traffic light stayed still. I could say that I was moving. Today I went to the beach and or the seaside, and I was moving relative to any marker that I could see on the seaside. For example, the cart that was selling hot tea. Okay, or we could say the ant was moving relative to the anthill, or we could say the bird was moving relative to the tree. I think you get the point. The point is it has to be moving relative to something that is not moving. Okay? That's not necessarily true, but we'll come to explain all the different scenarios later on. Reference point. To decide if you are moving, you use your chair as a reference point. So a reference point is a place or an object used for comparison. That's what it's used for, to determine if something is in motion. So that's what a reference point does. It decides if something's in motion. How does it do that? We'll come to find out. An object is in motion if it changes position relative to a reference point. Objects that are fixed relative to the Earth, such as a building, a tree, or a sign, make good reference points. Okay, so those objects make good reference points. Why? Because they are fixed onto the Earth. You may already know What happens if your reference point is moving relative to the Earth? Have you ever been in a school bus parked next to another bus? Suddenly you think that your bus is moving backwards. When you look out the window again for a fixed point, you find that your bus isn't moving at all. It's the other bus that's moving forward. Been there so many times. I remember that. So, for example, you're sitting down on the school bus and then you see like the other bus moving backwards, but you think your bus is moving forwards. We've all been there. Your bus seemed to be moving backwards because you had used the other bus as a reference point. So that's where the problem is. If you use another moving point as a reference point, you might be confused and think that you're the one moving. A bit like when we looked at the sun moving across the sky and thought, oh, it's the sun moving across the sky, when in reality it's the earth rotating. Okay, so let's have a look here. So there's the example that I've just mentioned. Because of the Earth's spin, the stars appear to move in a circular arcs across the night sky. Only the North Star remains in a fixed position. Historically, sailors have used the North Star to help them navigate. Yep, they sure have. We also have a Southern Star in the Southern Hemisphere. We talked about that quite a lot in New Zealand and Australia. So here's an example. We've got a boy who's sitting in the car, and then we've got what appears to be a car behind or next to them, and it's moving. Or maybe their car's moving. I think that's the question we have to answer. Interpret the photos. So we've got to try and figure out what's going on. Did the car the boy is in move, or did the car in the background move? Explain your answer. Well, a bit of a tricky one. There's a flag, and here it is. So that's the flag, and the car, the red car, appears to move relative to the flag. So we've got quite a few stationary reference points, and the red car appears to be moving. So I'm just going to say the red car is moving. Red car is moving, and the reason for that is quite obvious, really. Relative, horrible spelling. Relative to stationary reference points in the background. So what that means is relative to everything that is still, that is not moving in the background, the red car is moving. Identify what objects in the photos make good reference points. Well, I did talk about one already. The flag is a good reference point. The whole building is a good reference point. The lawn is a good reference point. So the grass is a good reference point. The school sign is a good reference point. The tree is a good reference point. So basically anything in the background that is not moving is a good reference point. I'm just going to say a few here. Tree, flag, school. I'm sure you can think of others. Okay, let's move on. Relative motion. Here are a couple of scenarios that are quite interesting. If you are traveling in a train and the train is moving at 100 kilometers per hour compared to another passenger, are you in motion? So you're both moving at the same time, you're both sitting next to each other. If you look at them, they're still there. You go to sleep, you open your eyes again, you look at them, and they're still there. Have they moved relative to you? Have they moved compared to another passenger? And the answer is no. Relative to you, they haven't moved. Relative to another passenger, they haven't moved. Even though everyone on the train is moving at 100 kilometers per hour, relative to each other, they haven't moved. However, relative to, now we have the same scenario here. If you're traveling in a train and the train is moving at 100 kilometers per hour, compared to someone standing outside, are you moving? Yes, you are. You and the train and everyone on the train is moving. Everyone is moving at 100 kilometers per hour. Okay, here is some questions to check your understanding. We've got the first question that says, a tree is what relative to the earth? So a tree is not moving relative to the earth, so what do we say about that? We say it's stationary. Stationary just means not moving. A tree is stationary relative to the earth. How about relative to the sun? Well, as we have explained before, the earth is moving, everything on the earth is moving relative to the sun. So it is in fact in motion. And motion just means moving. Okay, right, moving on. Relative motion. So here we have a wee paragraph about relative motion. If you use your chair as your reference point as you sit and read, you are not moving. If you choose another object as a reference point, you may be moving, maybe. Let's say, for example, you're sitting in the back of the car and you're reading a book. You're not really moving relative to the driver or the passengers or even the chair, but you are moving relative to anyone outside the car when they're watching you. Suppose you use the sun as a reference point instead of your chair. If you compare your position to the sun, then you are moving quite rapidly. In fact, 30 kilometers every second. Did you know that? 30,000 meters every single second you are moving. Yeah. So obviously, once again, we're talking about reference points here. The reference point in this scenario would be the sun. Okay. Interpret the photos. Are the people moving relative to each other, or are they moving relative to the objects in the background? Let's have a look. So let's just make that a bit more clear. Here we have a person, and let's just give him some eyelashes, one ear, and another. And here we go. Beautiful hair that's blowing in the wind. Are the people moving relative to each other, or are they moving relative to the objects in the background or on the ground? Explain. Well, I think it's quite obvious that those two people are on the same ride. So it looks like one of those rides on the playground, you know, those things that go around. And they are together on the ride. So obviously they're not moving relative to each other because they are moving together. A bit like that train scenario or that plane scenario, they are together. So are they moving relative to objects on the ground, or are they moving relative to each other? They, I would say, are not, they are not moving relative to each other, but they are moving relative to objects. Oops, what happened? Let's go back. Objects on the ground as their position. Remember, what makes something move? The position changes. As their position changes relative to those stationary objects. So the position is changing. Oops. Oh, come on, stop doing that. Objects. How is your choice of reference point important when describing motion of people? It literally determines if they are in movement. The reference point determines if they are moving or not. If I choose the actual ride, the actual whatever contraption they're on as a reference point, then they're not moving. But if I choose any object in the background, then they are moving. So I'm just going to make that really simple. I'm just going to say the reference point determines if the people are moving. The reference point determines motion. That's even simpler. Okay, so the reference point determines if things are moving or not. Measuring distance, are we there yet? Oh, wow, okay. To describe motion completely, you need to use units of measurement. Of course, that's related to movement. If you are moving, how far are you moving? How fast are you moving? What is your velocity? What is your speed? Possibly, what is your acceleration? That has to do with, now we've come to talking about units. So we do need to talk about units. Scientists use a system of measurement called International System of Units, or in French, System International. SI, distance, is the length of the path between 2 points. The SI unit for length is meters. Okay, the distance from the floor to the doorknob is about 1 meter, for example. Your height is probably about 1.6 to 1.8 meters, and so on and so forth. Scientists use other units to measure distances much smaller or much larger than a meter. For example, the width of a spider over here is measured in centimeters, and the word centi or centi just means tenth. All right, means 100. Oh, sorry, centi means 100th. Blind moment. The prefix centi means 100th. So, for example, there are 100 centimeters in a meter. And so there are 100 centimeters in a meter. For length smaller than a centimeter, we use millimeter, and the prefix milli just means 1,000th. Okay, there are 1,000 millimeters in a meter. Distances much larger than a meter can be measured in kilometers, and the word kilo just means 1,000. That's why we have kilometers, kilograms, kilobytes, yeah, kiloliters. Can you have kiloliters? Yes, you can. So kilo just means 1,000. I can have kilo dinars if I wanted to. Okay, let's have a look at these units over here, and hopefully you remember some of those from maths. Let's have a look. Fill in the following common conversions for length. 1 meter equals how many millimeters? Well, we know that 1 meter equals 100 centimeters, and each centimeter is 10 millimeters, so that's going to be 1,000 millimeters. And 1 meter is how many centimeters? Well, we just talked about it. Remember when I used to bring Mrs. Meter to the classroom? My stick with the eyes drawn on it. So that's 100 centimeters right there. 1 meter is 100 centimeters. 1 kilometer. Remember 1 kilo, 1 kilometer, kilo, meter, kilometer. Kilo means 1,000. Meters means meters. So we have 1,000 meters here. Kilometers just means 1,000 meters. What is the distance in centimeters from point A to point B on the spider? Now, I do have the book, and I remember measuring this, and I think it was about from this point here up to this point here, I think it was about 7 centimeters from memory, so I'm just going to go ahead and write that in. How many of these spiders would you fit side by side, excuse me, in the length of 1 meter? So we have 100 centimeters, and we're trying to figure out, I'm just going to use red for a bit. We're trying to figure out how many of those spiders can we fit in. So the way to do this is by dividing by 7 centimeters, and that is approximately 13, or is it 14? Let's have a look. 100 divided by 7, 14 spiders. Now, it's actually 14.3, but you can't really do a third of a spider. So, 14 spiders. Okay, let's carry on. And here we have assess your understanding at a view. What is a place or object used for comparison to determine if something is in motion? What makes us decide if something's in motion? Come on, easy peasy lemon squeezy by now. That is a reference point. Reference point. Why is it important to know if your reference point is moving? Literally, so you can determine if your motion is going in the correct position or not. To make sure you are measuring motion accurately. Because if the reference point is moving, then you can't really measure the motion accurately. Let's say, for example, I'm moving away from a car, and I want to know how much I'm moving. So I'm moved away only 5 meters. But hang on, the car has moved like 20 meters. So now I don't know how much I moved. So make sure that the reference point, if you're measuring distances, that it's stationary, but there are scenarios where the reference point is moving, and that's fine. We can also work around it. Okay, and finally, I get it. Now I know that an object is in motion if what? if the position changes, and then there's another part to that, if the position changes relative to a reference point. If the position changes oh, it's so hard to write on glass. That's supposed to be an O. Position changes relative, not relative, relative to, let me try my best handwriting on this glass, to a, not bad. Okay, there we go. Fantastic. Let's see if there's anything else we need to do. Measuring distances. To describe motion completely, you need to measure the distance. The distance is the length of the path between 2 points. So we're just recapping now. This is the plenary. And measuring and distance, the SI unit for distance is meters, but we can use any of these. And in fact, we can use millimeters, centimeters, kilometers, or meters. And in some places, they use miles, and they use yards, and they use feet. Yeah, so there are others as well, but we won't go into it. So there are different units of length. The standard international one is meters. What does milli, centi, and kilo mean? Milli means 1,000th, centi means 100th, and kilo means 1,000. So milli means 1 over 1,000, while kilo means 1,000. And how do we convert units? Well, you can look this up if you want to, or you can pause the video and take notes of this. However, if you're going from something big to something small, then obviously you're going to multiply. And if you're going from something small to something big, then you're going to divide. An example of that would be, say I have, for example, I have 100 centimeters. How many meters do I have? I divide by 100. But let's say, for example, I have 2 meters. How many centimeters do I have? I'm going from big to small. I multiply. So 2 meters equals 2 times 100, 200 centimeters. Let's do some examples. 400 centimeters is how many meters? Well, we know 400 centimeters over here. How many meters? So we are going over here. So we have to divide by 100. So that's going to be 4 meters. 7,000 meters is how many kilometers? 7,000 meters. So that's over here. 7,000 meters. How many kilometers? Divide by 1,000. So that's going to be 7 kilometers. 90 millimeters. I want you to pause the video. I want you to try and do this and then check your answers. 90 millimeters is how many centimeters? I know each centimeter is 10 millimeters. Each centimeter is how many millimeters? 10. So if I have 90, that means I have 9 centimeters. 44.3 millimeters is how many centimeters? Once again, each centimeter is 10. So all I have to do here is divide by 10. Divide by 10, and that gives me 4.43 centimeters. And 0.35 kilometers is how many meters? 0.35 kilometers. So that's, let me put that over here, 0.35. What do I have to do to get meters? I have to multiply by 1,000. So that is going to be 350 meters. Okay, and if you're not sure about these, make sure you go back through the video, or I would suggest go to iExcel, or is it XLI, and get some practice with unit conversions. Okay, so it's called unit conversions. Why is it important to know if reference point is moving? We've already established this to get accurate measurements of whether an object is in motion or not. Okay. Give examples of reference points that are stationary relative to the Earth. Interesting. This requires a bit of thinking. Technically speaking, an object that is not moving relative to the Earth would be the center of the Earth, possibly the North Pole, the South Pole. But I think, generally speaking, what they're talking about here is every single object on Earth, because it's fixed onto the Earth. However, it's also rotating around the Earth. So we're just going to assume that trees and mountains and such are all reference points. Another reference point of an object that is stationary relative to the Earth, and one that's been used for many, many years by navigators and explorers, is the stars. So the stars seem quite stationary relative to the Earth, which is why you can use them when you are navigating. Okay? When determining the motion of the planets in the solar system, what is a good reference point and why? Well, it's actually in the name, solar. Solar system. Solar means sun. So a good reference point would be the sun because we are moving relative to the sun. There you go. Since we are moving relative to the sun, it would be a good reference point to use. That way we can measure our change relative to the sun, which is stationary. And that's that. Okay, boys and girls, I hope you enjoyed that. I will be uploading the next video shortly. Please make sure you take care during the National Day holidays. And over and out. I'll see you in the next video, inshallah.